Next, we'll determine the order and rate constant for a reaction. Consider the reaction between nitrogen dioxide NO2 and carbon monoxide CO. This is going to NO and CO2. The initial rate of the reaction is measured at several different concentrations of the reactants, and the tabulated results are shown here. From the data, determine the rate law for the reaction and the rate constant K for the reaction. There are two different methods for determining the rate law for a reaction. The first method is to hold the concentration of one species constant while changing the concentration of the other and examining what happens to the rate. The second method involves plugging in a ratio of rates and concentrations and solving for the exponent for each species. We'll examine the first method first. Again, our reaction is between the starting materials NO2 and CO. We're going to hold CO, carbon monoxide, constant first, and we see that the concentration of nitrogen dioxide is doubled. When the NO2 is doubled, we see that the rate is quadrupled, or we get 4 times the rate. Next, we hold the concentration of NO2 constant and we double CO. So we see that when we double the carbon monoxide concentration, nothing happens to the rate. So just to confirm, again, we double the rate of the NO2 and we half the rate of the CO, because that shouldn't change anything if we're observing the same type of situation. Then we see that the rate again quadruples, so we see that the carbon monoxide concentration has no effect on the rate, but doubling the concentration of NO2 quadruples the rate. So writing the rate expression to reflect those observations is rate is equal to K times the concentration of NO2 squared, so it's second order, and CO to the 0, so it's 0 order. And since it's not dependent on the concentration of carbon monoxide, we can simply express the rate as K times the concentration of NO2 squared, because when we double the NO2 concentration, we 4 times the rate. If we have trouble determining the rate law by examining the data, we can use the following method to determine the rate law for each species. Take two different data points for each species and plug in the rate at each of those data points, the ratio of those rates on the left, and the rate law at each concentration for the respective data point on the right. For example, for NO2, we choose these two data points. At 0.20 molar, our rate is 0.0082 molar per second, and at 0.10 molar, the rate is 0.0021 molar per second. So, by choosing those two data points, we plug in the rate at 0.2 over the rate at 0.1 is equal to, we put the rate law on the right at each concentration, is equal to K times NO2 at 0.2 to the N is what we're looking for, divided by K times NO2 at 0.1 to the N. So here we have 0.0082 molar per second divided by 0.0021 molar per second is equal to K times 0.20 molar to the N divided by K times 0.10 molar to the N. So we see that the units cancel out on the left and on the right. The K's cancel on the right, and we have 3.9 is equal to 0.20 over 0.10 to the N. So 3.9 is equal to 2 to the n. So to get our power out, we take the log of each side. The log of 3.9 is equal to the log of 2 to the n. We can use log rules to say the n log of 2 is equal to the log of 3.9. So now we can get n on a side by itself. N is equal to the log of 3.9 divided by the log of 2. So we get n is equal to 1.96, which is close enough to 2 because we prefer not to have a fractional rate equation. And the rate equation generally isn't a fraction, though we can have exceptions to that. Now we'll perform the same calculation for the carbon monoxide. The rate at data point 3 divided by the rate at data point 2 is equal to K times carbon monoxide concentration at point 3 over the carbon monoxide concentration at point 2 times K to the n. So we get 0.0083 divided by 0.0082 is equal to K times 0.20 molar to the n divided by K times 0.10 molar to the n. So these are just two data points for this species. It doesn't matter which two data points you pick as long as you're changing the concentration. Okay, and so now we can solve. So we get 1.01 is equal to 0.20 over 0.10 to the n. So 1.01 is equal to 2 to the n. We can take the log of both sides here. The log of 1.01 is equal to log 2 to the n. Using log powers, we can bring the n in front. So n is equal to log 1.01 divided by log 2. So n is equal to 0.01, which is pretty close to 0. So we see that our rate is equal to K times NO2 to the second times CO to the 0 is equal to K times NO2 squared, which is the same rate law we got from observing the data.